We've covered quite a bit of ground now. We've had you write some rungs of logic, and we had you do some logic that remembers, meaning, well, let me give you an example. You want to put the machine into the automatic mode, but to put it into the automatic mode, it has to meet certain prerequisites. All of the motion action has to be returned to the home position. All the safeties have to be met. There's a number of conditions that have to basically be at the start or the initial state in order for you to put it in the automatic mode. You just can't put it in the automatic mode no matter what state the machine's in. However, the conditions or prerequisites to go into the automatic mode aren't going to stay there the whole time you're in the automatic mode, or as we say, the auto mode, which means you have to have logic that is true when it's ready to go into the automatic mode, but the automatic mode has to stay there even though the conditions that allowed it are no longer there. Now you have other things that can happen that knock it out of the auto mode, like stop or go to manual or some sort of fault. But we have to have logic that looks at a number of conditions and then determines the prerequisite to go to automatic, even though those conditions and prerequisites change. Because once you start the machine and the slide cylinders start moving, it's no longer in the home position, but you want to stay in the auto mode. Latch and unlatch is one way to do that. Because the latch instruction, if the rung's true, it turns on the auto mode bit, but the rung doesn't have to stay true, correct? Another way to do that was something we call seal-in logic, and that is that we have the prerequisites and then we turn on a bit. When that bit comes on, we then examine that bit with other instructions that bypass the conditions that are more fluid and don't stay there, and we seal in that state with logic. The advantage is that everything required to initiate the state and hold the state are all in one rung. Whereas with latch and unlatch, if you had a 1,000 rung program, the latch instruction could be in rung 11 and the unlatch in rung 783, nowhere near it. Whereas with seal-in logic, everything that controls the state of that bit is all in that one rung of logic. Latch and unlatch is much easier to write. And as beginners, most folks write their code with latch and unlatch. But that's frowned upon. We used to say when you use latches, you have to unlatch the whole world, which means if you use all these latches, then you have to go back and figure out what you latched and then unlatch it somewhere. Whereas with seal-in logic, the whole complete process is in one rung. So now we're going to look at seal-in logic. Let's do it. Seal-in logic with true-if on, true-if off, and energize output instructions. This is just another method of creating logic that remembers. And this is where you stopped with your project. I'm online now, and in the manual it says to go offline. First it says to save. You should actually save your project more often probably than I say to in the manual, and come up with your own naming method so you know what order to do them in. In what order to go back to them in. You could have started from the beginning with 000. On your 100th save, it would have been 099. You had a number that gave you the exact order. The problem with that is the files show up in alphanumeric order. You would have to come up with some kind of nomenclature at the front of the file name if you want them to show up in order instead of searching down and looking for a particular number. Nonetheless, we'll go offline to do these edits. We're going to work with rung 2 here. In the manual, I showed you several different ways of editing. I'm just going to drag this down and drop it there. And then I'm going to drag this down to that Mimi, and then drag the blue bar over to this Mimi. You see the difference between this is distribution Mimis between instructions. They look slightly different than when you drag down an instruction. See, they're round. They go from square to round. But when you did this, they're oval shaped. They're rectangular and oval. Then I had you click here to bring the focus on this branch. And then click on, just single click on a true if on, and it pops it in there. By the way, this is on roughly page 144, 145 in the manual. Then we had you grab this tag, not the instruction, just the tag, drag it over here to this true if on. And then there's several ways that you can put the tag here. I'm lazy, so I grab a copy of a tag that's close, then double click, backspace, and change the bit. So there, I arrived at the same result that's in the manual with a slightly different approach. There's lots of ways that you can get the tag in there. Remember, it is just text. There's nothing magical about drilling down into the data word and grabbing that bit. It's just text. So I had you add the tag to the true if on instruction. Save your project as beginner L, your processor number CLN. And just in case you've lost track of what that means, save as, and go down here and I highlight the unique part of the name, and this is going to be CLN. Now I put a space there because if I put an I or an uppercase I, you can't tell the difference between that and the lowercase l. So I put in an underscore, then uppercase I, lowercase n. Beginner L31 CLN. Save my project. All inputs off. Download and go online in the run mode. Communications, who active. Select the processor, download. Remember, this is RS-232, 38.4K baud. Very, very slow compared to Ethernet. If you're working with an Ethernet processor, you have a good thing. As I've said before, I'm doing this with RS-232 because I want to continually feel your pain if you're using RS-232 and not Ethernet. Okay, we've introduced the OR function, not the OR instruction. There is a logical instruction. In ladder diagram, this is the OR function. If this is true and this is true, or if this is true and this is true, then this. Or you could say, if this is true and this is true, or this, then that. Typically, when you say it that way, you need a parentheses. In other words, you say this and then in parentheses this or this, then that. So this is the OR function. And if you were thinking of this in terms of electrical, if these were switches and this were a relay coil or a light bulb, this switch would have to be on, and then either of these two switches would turn on that light. This switch or this switch and this switch will turn on that light. We have two approaches to controlling a bit in memory that influences the state of a field device. One for local 1O data 0 and a completely unique approach for local 1O data 2. Before we continue, let's add some descriptions to the memory locations to make the process more efficient. Now I'm going to do this one right here. I'm going to right click, edit main operand, description. I'm going to type in start. Then I'm going to hit the green check mark. And now you see we have a description. I'm not going to make you watch me enter the rest of them, but I am going to enter them so my screen looks like yours. Okay, I've added start and stop. And then there was a question in the manual that stated how many locations in your ladder logic diagram did that description appear. Well, this description appeared in 2 places, and that would be the same for both of them, but we specifically asked for this, so the correct answer would be 2, or rather the answer that we were after was 2. But really the only reason we ask questions like these is for you to take note that when you added this description to that tag, module defined tag, or any tag, the description will appear above it any place that it is in the program. If this tag was used 78 times in the program, stop would appear 78 times every place you use that tag. I also had you add descriptions on the output bits, 1M for motor 1, 2M for motor 2. Also, when I added the descriptions onto these bits, which aren't the same bits or tags as these, I included the motor nomenclature, stop 2M and start 2M, and I asked you why you thought maybe that I did that. Well, 2 reasons. One is that's more descriptive. It makes more sense. And the other is I didn't want the exact same description on both of these. And you can do that. You could have put stop on as many different tags as you want, because RSLogix 5000 does not force you to make each description unique to that tag. Stop could be on hundreds of different tags, the description for all of the data bits. Of course, you don't want to do that because the idea of descriptions is for us. The PLC could care less about descriptions. The descriptions are for us. In the manual, on page roughly 148 or 149, something like that, there's a couple truth tables. After you have your logic in this form, you download, you're in the run mode, we ask you to operate your switches, input 0 and input 1, in the order shown. And the first truth table is for input 0, input 1, and 1M. The second is for input 2, input 3, and 2M. We'll start off by turning input 0 off and input 1 on. And then you were to write down the state of 1M. As you can see there, that I have this input on and that input off. And that both of this input is on, this input is off, and this bit is off. Then we had you turn on input 0. Now they're both on. That's the second row in the truth table, on, and the answer would be on. And then we had you turn off 0. So it is now bit 0 is off and bit 1 is on, and the output is still on. Then we had you turn off input 1, so they're both off, and now that output is off. And then we had you turn on input 1 again, and it's still off. So when you look at that first truth table, and I'm going to say all 3 states, starting with 0, off, on, off, on, off, on, off, off, on, off. Now the reason we do that is because we want to compare it to the third rung, rung 2, with the exact same sequence, only with input 2 and 3. With input 2 off and input 3 on, so you can see here that 3 is on, 2 is off, and this is off. And that's written already for you in row 0 of the second truth table there, just to show you what it's supposed to look like. Then we turn on input 2, and you see that the output is now on. Then we have you turn off input 2. Turn off input 2, and you see there's 2 right there. It's on, it's off. With this on and this off, this is still on. Now the reason it's still on is because of this OR. It's sealing itself in. The state of this bit is on. So when it reads the logic, true, false, true, turn this on. So this will stay on until you make this go false. Anyway, we're still doing our truth table. Then on the next one, it wants input 2 off and input 3 on, which is what we have right here. And the bit is on. That's the one we just did. And then both of them off, 2 and 3 off. And the bit is off. And then turn input 3 on, and the bit is still off. When you look at your two truth tables, they should read 100% identical. Row 0 on both of them should be off, on, off. Then the next column, or row, I'm sorry, is on, then off, on, off, off, and off, on, off. Now the reason we did this is to demonstrate to you firmly that these two approaches to controlling an output device are identical. There is one minor difference, however, though. If I turn 2M back on, then off, and if I turn on 0, then off, both motors are running, right? Or both outputs are on. If I put the controller in the program mode, and then come back to the run mode, notice what happened. Let me do that again. I'm in the run mode now. Pay attention up here in your online toolbar. Both of these bits are on. Remember that that's one bit. These two rungs, remember that the highlight shows you the state of the bit in memory, not true false. So these are not 2 bits. That's the same bit. It's just showing you that that bit is on, this bit is on. So I'm going to put it into the program mode. Nothing changes, but remember the data table stayed exactly as it was when you left the run mode. However, watch up here, remote run, you lost that bit. So that's the difference in these two approaches, is if you do a set reset or latch unlatch, the bit will stay in whatever state it was in. It'll stay on if you go into the program mode and come back to the run mode. But with this logic, it will not. Right below the truth tables, there's 2 truth tables, one on the left and one on the right. The one on the left is for the examples directly below it on that page, roughly page 148, 149. The truth table on the right is for the following page that has the 4 illustrations of the logic. We did the same for both groups. On the first group, down at the bottom of the page, it says 1, 2, 3, 4. Start 1M, return the input to its original state. Stop 1M, return the input to its original state. And that describes the 4 pairs of rungs above in their different states. Then on the next page, we did the exact same thing with rung 2 there. We showed it in 4 different conditions. And again, we did this to demonstrate that this code works the same as this code, with the exception that if you leave the run mode and come back, if this bit was on, it will not be on after you return. Now on my on my hardware trainer, my lab station, I have a digital field device simulator that has 6 toggle switches and 6 push buttons. Those 6 push buttons are also lit as a separate function. They also fill the purpose of outputs, to display the change of state of outputs. Now I can see the LEDs on the output card on my controller, but it's much easier to work with if you have lights on your box or on your simulator instead of just looking at the LEDs on the controller. But my 6 push buttons are wired in the same circuit as the toggle switches right next to them. Input 1 through 5, the normally open contacts on those push buttons are wired in parallel with the toggle switches. You can have a maintained on, maintained off, or normally open. So you just leave the toggle switch off, and then when you push the button, it momentarily goes on. Input 0, the very top one, is a special enhanced input in that push button is wired in or in the circuit with the toggle switch, so when the toggle switch is off, then the push button is a normally open. When the toggle switch is on, then the push button is connected as a normally closed. So that means for input 0, you can have maintained on, maintained off, normally open push button, normally closed push button. And in many cases, it's much quicker. The learning process is much quicker if you don't have to stop and do the mental gymnastics on which switch does what. Am I supposed to toggle this off and then back on, or what am I supposed to do here? So you can use push buttons instead of just the toggles. If you were asked to speak these rungs of logic in front of you, in general terms, you might say rung 0 says, that's this rung up here, that if local 1 I data 0, that bit in memory is on, and if local 1 I data 1, that bit in memory is on, then turn on local 10 data 0, that bit in memory. Remember, there's no false execution here, so there's no else. This rung reads basically the same with a change in the on and off status of the sentence. So rung 1 says that if local 1i data 1, that bit is off in memory, and if local 1i data 0, that bit is in memory is off, then turn off that bit in memory. Rung 2 says that if local 1i data 3, that bit is on in memory, and if, in parentheses now, local 1i data 2, that bit in memory is on, or if local 10 data 2, that bit in memory is on, close parentheses, then turn on local 10 data 2, that bit in memory. Else, turn off local 10 data 2, that bit in memory. This exercise introduced the AND function and the OR function in logical terms. Why is there not an else in the text description for rung 0 and rung number 1? That is because in rung number 0 and rung number 1, those instructions, those output instructions over here, the action instructions, latch and unlatch, they have no false execution, so there is no else. This has a false execution. So we're saying if this rung is true, turn that on, else, if the rung is false, turn it off. For the sake of clarity, let us slim down our logical statements. The logical operators are in bold. We could use the descriptions in place of the tags that point to the actual memory locations, but the descriptions can be assigned to more than one pointer, that is, to more than one tag or variable. However, we can create new tags that look like descriptions and alias them to the actual members of the module defined tags. That's what we're going to do next. This is roughly page 151, 152 or so in the manual. There are several ways that we can go about this. We can edit the tags on our instructions of our existing ladder logic diagram, or create new tags. Either way, the tags have to be created before you can use them. You need to open your controller tags to verify that there are no tags in there except the module defined tags. Double click here. Okay, now we do have these other tags in there, so we're going to delete these. These are not being used. Now you might be using these, okay? If you're using some other I/O configuration, then don't delete these if you're using these. I'm going to delete these because I'm not using them. So I drag the mouse through all of them and hit the delete key. Now it won't let you do that if these tags are being used. I'm online in the run mode. So the only way you can delete tags in the run mode is if they're not being used in the ladder logic. Now I had you add some description. We're in the controller tags. Expand local 1i data. I'm going to change these though to start 1M, stop 1M. Now I already had these tags in there, and you should too if you've been doing your lab projects first and then watching the videos. If you're watching the videos first, well, you don't have any of this done. How many members of this module defined data type have descriptions? 4. Now you know where to find the descriptions if you want to edit them apart from the ladder logic diagram itself, because remember, you can do this right in the ladder logic diagram by right-clicking and then changing the operand. Now you see that the descriptions have changed. They did say start, stop, stop, start, but now you have the 1M after it. Open your program tags to verify that there are no tags in there except the 2 that you created earlier and they're not using now. Okay, I had you save your program as aliased. File, save as, aliased, and go offline. We're going to examine editing an existing tag versus creating a new tag. And we're going to do this with the logic that we have. We're going to do it offline. If you make a mistake with tags online, you can't edit them once they're created. You have to go offline, delete them, or you can, online, you can take them out of the code so they're not being used, then delete them, and then redo them. Or go offline and edit them. So what we want to do is up here with this tag, we want to double click on it to open the tag name. Then type in start, and of course you cannot use spaces, underscore, and we'll do something slightly different just so it's different, just so it looks different. Start motor 1. When we mouse over that, you see it's an undefined tag. That tag doesn't exist. So notice when you mouse over the tag name, RSLogix 5000 does not find it in any of the tag databases, controller or program. It must be defined to make the e's disappear and have the rung of logic self-accept in the offline mode. In the offline mode, the e's will disappear as soon as the rung is right. The rung is not happy because it has no idea what start motor 1 is, or what it means. It is undefined as the message indicates. The following pop-up is standard when you right-click on an undefined tag. RSLogix 5000 knows that it will be a new tag if you define it. If you right-click on this tag, it knows that you want to create a new tag because you right-clicked on a undefined tag. If we drop down, go to Start, and we drop down, we can pick whether it goes in the controller tag or the program tags. So you see this little symbol, looks like a controller with a little arrow on it, and that's the name of the whole project, so to speak, beginner L31. That's the controller tags. So you can pick the scope right here. Keep in mind, if we pick main program, the next time we come here, it's going to show main program. If we pick the processor tags, the controller tags, then the next time we come here, it's going to show the scope of whatever you picked last time. So we wanted you to pick main program and then create. So this tag now is created in the main program. When you mouse over, tag, start underscore motor 1, data type Boolean, scope, main program, value 0. Because the instruction, true if on, only operates with the state of a single bit in memory, RSLogix 5000 assumes that you want a Boolean data type. That's why when we right-clicked on it, it came up with Boolean selected, because it's smart enough to know that you cannot put any other type of tag or data type on a true if on, true if off type instruction except for a Boolean type. But you could drill down and pick a bit from another tag. So we'll show you what I mean. If we had a dent tag in here, which we don't, so we'll pick on one that is a dent. So here's integer, single integer. We can pick on any one of these. So see, I can go pick a bit to put on that instruction. Now we don't want to change it. We want it to be what it was, which was start motor 1. My point is that not only does RSLogix have type forward, it tries to look forward to see what you want next and pops it up there, but it also knows what you are probably going to pick. It tends to fill up the fields in the pop-up with default values based on the context of what you're doing. On the other hand, the scope of the tag is what you need to be thinking about when you define the tag. The controller tag database was last selected, and this pop-up came up with your last choice. If you were to select create without changing the scope, the tag would have been created in the controller tags database and not in the program tags database where we want it. The ladder logic diagram will execute the same regardless of which database the tag is in. But if we want to reuse the program, we need the tags isolated from all of the other programs, and we do that by creating or moving them into the program tags database. We had you right click on start 1M. That's our new tag. Then it says compare this list of actions grayed out or otherwise to the list on the previous page when you queried an undefined tag. These lists are always context sensitive and will not offer an action that is not available. It might be in the list but will be grayed out if semi-relevant, such as trend. You see trend here is grayed out. Select edit properties. The pop-up looks identical, but the action is not even close. So we'll go down here. You're not creating a new tag in the main program tag database. You are modifying an existing tag. Remember, we selected edit properties. We're not creating a new tag. We already created start motor 1. Any changes here will change the tag on any instruction where it is used. So if you use this start underscore mtr1 tag on 20 different instructions, anywhere that you edit it, it is edited for all instances of that tag. If you change the name here, it is not a new tag, and you have modified it in the database, and it will appear changed at every point of usage in your project. You are changing the instance, not the reference. We're not creating a new tag. We're editing an existing tag. We just happen to do it right on the instruction. This is not a copy, paste, edit procedure. Okay, drop down and select alias. Alias 4. Now you could have typed in, we'll kill that and do that again. Edit properties, alias. We could just type in here LO for local, and now we're already halfway there. So we wanted to drop down to local 1i data. Click about there and you get the bits. And then pick bit 0. Apply. Now you see we have a description start 1M that is describing the tag start motor 1 that is alias to that input in memory. You could have also just edited the bit after this to complete it. In the manual I showed, you can just start typing in local :1:i .data .0, and when the whole thing appears, you know, in reverse video, then you just hit enter. I would do it the simple way, the way I've been showing you for now. Later on, if you want to get a little loose and fancy with how you do things and you make a mistake, it's not a problem. You'll know how to dig yourself out of it. For right now, though, I would keep it simple. I hope that you notice the progression of elimination of tag names as you added each character. For instance, if we were to, we're offline, so we can add another rung, add another instruction, and we can type in S, nothing happens. T, and it comes up with the very first tag in the database that begins with ST. Now it's in alphanumeric order, so we want, let's say we want stop 2M. So we type in an O, P. Now notice nothing popped up. Why? We don't have any tags that begin with STO. We have descriptions but not tags. So you don't want to get tangled up with that. So instead, we'll take the one that we have up there, start. See, it pops up. Now if we did have a tag named stop, which we will here shortly, then we'll come back and do this again. For right now, I'll just delete this and continue. Typically, you will have hundreds of tags in the databases, and when you type in just the first few characters followed by selecting the drop-down list, this will put you very close to the one that you want in the list. That's what we're trying to show you here. It's not working out real well because we just don't have that many tags. So we'll try this again later when we have more tags to work with. Do we need the description and the alias both? The alias start 1 motor is permanently tied to local 1i data 0, whereas the description is not. So we can double click on that. Well, we'll go to edit. That's a description. We don't need that. Matter of fact, I'm going to delete all the descriptions right now. Now you see they're gone. In rung 0 and 1, notice that we have local 1i data 0, local 1i data 0. What's the difference between this tag and this tag? Functionally, nothing. Start motor 1 is aliased to local 1i data 0. But if we use local 1i data 0 someplace else, it doesn't bring the alias with it. Matter of fact, we could alias this to something completely different. We'll just do that for grins. Okay? So we're not going to edit the properties. What we're going to do instead is we're going to create a new tag, and we're going to call it start first motor. Right click, new, alias, LO for local, drop down to the data, bit 0. Now look, local 1i data 0, local 1i data 0. These are identical base tags but with different aliases. The alias is attached to the base tag. The base tag is not attached to the alias. Start MTR1 points to local 1i data 0. Start first motor points to local 1i data 0. You can alias as many tags as you want to point to the same base tag. Now, there's no reason to do that. This is what the point I'm making in this part of the lab is when we had, I'll delete that and then go back to the tag that we had. Now I'm cheating. I drug over Pt1, backspace 0, enter. Okay, we're back to where we were at now. And I asked what's the difference between this tag and this tag. Now you know. Then I had you take and drag, see this is local 1 I data 0, local 1 I data 0. So we can take this tag, mouse over, drag it down to a tag Mimi, it's kind of oval shaped, and drop it in there. So if you find yourself in this situation where you used a base tag, then you created another tag and aliased it to a base tag, and you want to make them all look the same, then just drag the alias tag over to where the base tag was used. Okay, open the main program tag database. Oh, by the way, I did have you get rid of these. So if I double click on that, hit delete, green check mark, double click on that, delete, green check mark, they're gone. We wanted to get rid of all of them. So I had you open up the main program tag database. Now this tag right here was one not in the manual, so I'm going to delete it. Then I had you click here and type in stop. And I'm mixing it up here compared to what was in the manual. In the manual we had start 1M, stop 1M. In this case I'm making it start motor 1 and stop motor 1. We could even spell it all the way out. We're not limited in memory for our learning procedure here, and we're not really limited in horizontal space. Go ahead and, if you want to do something slightly with the tag names, as long as you know where you're at in the procedure, by all means, experiment. Okay, then this one, it's already aliased for this base tag. Notice the C after it means that it's a controller tag. Here, I can type in LO, drop down, and then go pick the bit that I want, which is Pt1. Now you see this matches what's in the manual. You just created, named, and defined a new tag. So we just created stop motor 1. We aliased it to this base tag, this controller tag, module defined tag. Now return to your ladder logic diagram. Now you see it's not in there because the alias is attached to the base tag, but the base tag is not attached to the alias. So now if we double click here and type in ST, of course A is at the beginning of the alphanumeric sequence. O, see, it immediately pops up with stop motor 1. That's what we want. Hit enter. Then we can just take mouse over that and drag it down to the tag Mimi and let go. Okay. Edit the remaining memory locations addressed by instructions to display as shown in the illustration in your manual. That's roughly page 157, 158, and it's basically has you creating tags for everything and aliasing them to the base tags that were originally there. So we're going to create aliases for these 3 tags right here and this tag. And we might as well go to, well, it doesn't matter where we do it. I'm going to do a couple, but I'm not going to make you watch all of them. So I'll go over here and I'm going to type in, I can't type in 1M. Watch what happens when I do. See, well, watch it make a liar out of me. Nope. Failed to create a new tag. Tag name invalid. Okay, I don't know why it lets you go that far. You can't have a number as the first character. So typically what we do, if we do want a number first, you'll see this a lot. I don't like the way it looks, but I don't know how else to do it if you want a number first. Use an underscore. It'll let you do that. And just to mix it up, well, I'm going to leave it 1M. just to keep it simple. Okay, now that's not a new tag though, but it will accept it. So we go to new tag, alias, type in LO for local, drop down to our output data, bit 0. Okay, and then this one we can drag down here to that tag me. That one's taken care of. This one is going to be _2 uppercase M. Right click, new, alias, LO for local. Drop down to the output data. And we're going to make that 2. Create. Okay, and then remember this is local 10 data 2, local 10 data 2, so we drag this over here to that tag me and let her go. Now I'm going to cheat here. This is going to be stop 2M here, okay? But I'm going to drag this down, and then I'm going to change that 1 to a 2. The instant I do that, RSLogix goes, well, that's an undefined tag. So now I can right click, new, alias, LO for local, and this is an input, and we want bit 2. This one, and I'll just drag start motor 1 down, backspace 2, undefined tag, right click, new tag, alias, LO for local. Remember, you don't have to do that. Matter of fact, we won't do that this time. Okay, we'll just drill down to local, and we want bit 3. Okay, so now we got stop motor 2, start motor 2. Now we have tags. There's no descriptions here now. We have tags that are descriptive. Then we alias them to the actual base tag. Now let's say that you don't like the looks of the base tags. Well, we can go to Tools, Options, Display, Show Tag Alias Information. I'm going to uncheck the box, pull this out of the way, and hit Apply. See, now you have, well, we can't hit the geezer button. See, maybe you like that better. Personally, I don't, because when I look at these, I don't know if these are just base tags that are internal tags not attached to any I/O or what. Typically, I wouldn't do that. Show alias tag information. Apply, and they're back. It resets the screen size when you do that. So we'll geezer this back up so it's easy to see.